Okay, perfect. Hello, my name is Jakub Pawlak. I'm coming to you from the University of Kaiserslautern-Landau, which is located in southwestern Germany. I'm here because my professor, Carsten Behrens, couldn't unfortunately make it today. He would have loved to be here, but nonetheless, we wouldn't miss the chance to talk a little bit about our research and our group. So we are the chair of robotics, and we deal quite a lot in agricultural robotics as well. And this is what I'm going to talk about. So the first half of my presentation here will just show a little bit of our general work, show you a little bit the machines that we have in our group and that they have the specific goal of adaptability to the environments. And in the latter half of the presentation, I will talk a little bit about my own research, so in the direction of AI, and specifically in the direction of usage of synthetic data, which is my research. So to give you a brief overview of how the life cycle of our machines and basically AI applications in agriculture looks like, we try to make it a full circle approach. So we take the whole life cycle of a machine from simulation, from validation to navigation, the actual field work, monitoring and inspection, and we basically run this in a loop to get our machines ready. And to give you a little bit of a glimpse how that looks like, I'm just going to show some of our prototypes in the field of autonomous tractors, which we can see here, hopefully. Yes, so here we have developed some algorithms that allow for obstacle detection in the field. So you can actually be safe in operation while on the field, while there's obstacles, while there are people working next to the machine, and maybe even animals crossing or other machines or implements. So we used to do this a lot based on classical computer vision. So here we, for example, see an application of windrow detection, right? So the tractor was tasked of following the hay paths laid out by a harvester, and with the potential of application of collecting this. And for the first few tries that we did this, everything was classical computer vision. Like we see here, the tractor was equipped with sensors, with stereo vision sensors. That means that it had two cameras from which it could make a 3D reconstruction, which we kind of see in the upper left. So this is not just a normal video, but rather a 3D representation of the space. From this, we can make some maps. We always make maps to allow the robot to navigate in its environment and to denote the obstacles that are present. And in the end, we could reach pretty highly dynamic behavior with this. Yeah, this is a little bit more of that. This is from a harvester view now. And here the application was similar. On the right-hand side, you can see the 3D representation also. So the colors denote the depth in the image. And here we did a couple of different things with this, because the sensors are always tricky to use because they are noisy. The values that we get from them, they're not necessarily what we would always expect. So here there was a lot of Bayesian filtering involved. That means Kalman filters and whatnot to denoise the sensor data, so then it could actually yield the behavior that we wanted, which was also highly dynamic in this case. So yeah, that's a little bit of what we have been doing before, but also this is not where we want the journey to end. So this was mostly applications on the field itself. But we also want a holistic view, right? We want a tractor or a machine that is able to go from the hangar, from the machine hall, directly to the field and do as much work as possible without human action involved. So this is why we are going in the direction of fully autonomous tractors, for which we have a short demo here. This is our small John Deere tractor that we have outfitted with many, many sensors, like the aforementioned stereo vision, LIDAR, 360-degree cameras. So basically a full sensor suite that allows that to not only be autonomous on this, well, maybe let's call it simple, structured environment in the field, but also to get there by itself, right? So this is our concept of a fully autonomous tractor that is on the one hand, able to do field work as well as to do to get there on its own. This is currently work in progress, so we did some forbidden things by driving it on the street, so it wasn't really allowed, but it worked fine. It has GPS navigation. It can plot its own trajectories and get to the place where it needs to go. Of course, as of right now, it doesn't respect the rules of traffic yet. That's going to be coming in the next step. Okay, so this is our general purpose machine, but sometimes, we all probably know that agriculture has a lot of niche applications as well, so not everything can be covered with a general purpose machine, and that's why we also make very specialized robots for some applications that require it. For example, let's take a look here at our autonomous vineyard robot. So the situation in Germany, unfortunately, I don't know exactly how it is in France, but some vineyards in Germany are very steep. They have like up to 70% of slope, which here doesn't look so impressive, but once you stand there, it's actually quite a lot of slope. So here we have developed this machine that is able to be winched down like on a cable into these rows of wine plants to perform inspections and spraying tasks. That was a very, very involved challenge because it's a very dangerous application, because sometimes these vineyards or these slopes will end up in streets, actually, right? So there will be a street or a road going directly below the slope, and you have to make sure that this machine will always remain safe. Moving on to some other inspection tasks that we have in our group. Also regarding fruit plantations, and this is this little robot that we have made with a spin-off of ours. They're called robot makers. They used to be a part of our group, but now they have made their own company, which produces these kinds of robots for inspections. And here the goal was to perform inspection and yield monitoring in apple orchards, right? So this robot, it has tracks, it's off-road capable, and it's also equipped with a sensor suite, overlapping stereo cameras, so we can have a very, very thorough view of the apple plantations. And I'm just going to show it to you in action. Robot makers, they're a company who made the robot itself, and we were here doing the sensor and AI applications. So this is a robot that will autonomously follow the rows in the orchards and perform data collection. think next we're going to get a sensor view also. I would like to show you this before we move on. Yeah, we can autonomously change the row also, so that it can do the full orchard. Here we see the stereo setup and the LiDAR that is equipped. Yeah, here's the stereo view or the sensor view, and we collect this data, we save it, and we also save this 3D reconstruction always of the trees. That helps us to determine many parameters, for example, the growth of the wood, so we can go from season to season and actually analyze how much the tree has grown or how many branches it has or the leaf area of the tree. Okay, so this is maybe a little bit about the general vehicles and what we are up to in the realm of robotics itself, but maybe a common thread for all of them is that we do a lot of inspection work. And inspection work nowadays, if you want to do it at scale, requires artificial intelligence to do it at scale, because you don't want a human to look at every single piece of data that you have. But this whole artificial intelligence thing has come to prominence the last few years. It has one, I would say, drawback, maybe several, depending on who you ask. But my major focus is that it really requires a lot of data to perform nicely. So if you're talking with these neural networks and so on, we need on the order of magnitude of at least 1,000 images to perform like some task, right? Mostly it's way more than 1,000. Some of those networks are trained with millions of images. And how do we get those, specifically in the domain of agriculture? Because the issue is not just the images, right? We need a human to also mostly give them a label to say, okay, this is an apple, this is a healthy apple, this is a ripe wine. I don't know the word for wine thing, but is it ripe? Is it good? How do we do this? And this is very hard to get at scale with those thousands, tens of thousands, hundreds of thousands of images. And where we now come into this is digital twins and simulation. Because it turns out that you can nowadays do nice simulations of your environments. Here I'm going to show, for example, an example that we made, and this is like a digital twin of the application that we just saw. So here we made in simulation this apple plantation. We tried to recreate it. We tried to put some apples on there and actually train and evaluate algorithms on this data that we can collect. Because if you imagine, if we make this in the computer, we can take out all the data that we can possibly get from there, because it's already in the computer, right? The computer already knows which one is the apple, which one is part of the stem and whatnot. Yeah, so here's another example of that with a more concrete example. Here we see a simulated tractor. It was also, every machine in our lab has a digital twin and simulation, which we build up actually first. So first we always start with the simulated approach. We replicate exactly the sensors that we have on the machine in the simulation, and then we test it out there. And now we see we can also generate this data, right? On this lower image, we see a so-called segmentation mask, which basically assigns each pixel a class value. So for each element of the image, we know exactly what class this corresponds to. Here's in blue we show the tractor, while in green there's the row that we're currently interested in, while red was something else. So this is the kind of data that we can collect. Or in the upper right, we see an application that we did for sugar beet planting. And here we really made it in a semi-photorealistic way. And we could generate a lot of data, and actually a lot of data for different growth stages of this plant. But yeah, you see, especially on this upper left image, this doesn't quite look like the reality, right? There's still, I wouldn't call it photorealistic. There's a so-called sim to real gap, so a gap between simulated and real images, and neural networks also perceive that. So if we take the data just as is, we won't reach the performance that we would have gotten when using real data. It would be too good to be true, right? That we just get this data for free. But there's a couple of things that we can do to actually improve this, to get more value out of this synthetic data. And I'm gonna just talk about a couple of them. So the first thing that we did is so-called photogrammetry. We did this in this apple plantation, and hopefully you can see it. On the left side, we can see the real apple, which we just suspended in our lab, and we took many, many pictures of this apple, and then we did a 3D reconstruction of this. So basically, every fruit that you saw in this last video is a copy of a real fruit that exists in the real world, but we can replicate it 1,000-fold. We can have 1,000 of these in a simulation. And we know exactly where they are. Next up is maybe my favorite topic, and this is image-to-image translation using so-called generative adversarial networks. So basically, maybe many of you know already that a lot of algorithms in the image generation space also came to prominence recently. This is similar. So we take an image from the simulation. We see that on the left, this is how it comes out. We see that the sky is, well, not so nice. And in general, it lacks a little bit of detail. But we can take this image and put it in a separate neural network that is trained to make synthetic data look real. And we generate the ones on the right, which I think add quite some detail. And also to the human eye, they look a little bit better. We do this using this rendering-aware GAN architecture. So that means we take all the data that we get from this simulation engine. So this is not just the image as the humans see it, but also this segmentation mask or the depth image and other kinds of stuff that we get from the engine. Yeah, so it looks better to the human eye, but does it also actually perform better when we train a neural network with those data? And the answer is yes, it does. So what we do is always evaluate the real images, right? We train our algorithms here, for example, for segmenting out the path, so we know where our robots are supposed to drive. And we evaluate it always on the real data. Train it on fakes, evaluate on real. And here we see on the left this, you cannot see my cursor, okay. But the third column where it says unreal, this is a neural network trained just on this fake data, just how it comes out from the simulation. And compared to the ground truth that we see on the left, it's, zolala. And when we run our augmentation algorithm that we see on the right, we see a dramatic increase in performance. And when we take another step and actually mix a lot of this augmented synthetic data, and we mix in a tiny proportion, like 5% of real data, we almost reach the same performance as we would while using only real data. Okay, to maybe finish up my talk, I'm going to show you something that is very work in progress, but also a very promising approach. And this is going beyond this traditional rendering for simulation. So we have these new kinds of algorithms called Gaussian splats, and they allow us to do really, really photorealistic representations. So here I took like a scan of a plant, which is basically looks real, and I'm going to show you just an example of what we did with that. But maybe just let me quickly explain those Gaussian splats. Basically, we also take this point cloud representation, and when we drive around and collect these images and make these point cloud representations out of them, they're sparse. So you see these are 3D points, but there are gaps clearly in between them. But now some smart researchers, I think from France actually, they came up with a smart way to smudge them out, to basically blur those individual points in a smart way so that we can kind of close these gaps. And what we end up with is something like this. This is our campus that we have reconstructed from using this Gaussian splatting technique from video. So here it looks actually like a video, but it's kind of hard for me to show this. But actually you could go ahead and manipulate or turn the camera in any way you wanted, and you would still have like a representation. So you can basically, with a neural network, render a simulation, so to speak, instead of relying on tools as Unreal Engine. So how can we use this? Here we see this the scan as it was before. We put this into this Unreal image, and we're making a tool out of this for making these annotations that we were speaking about. So now we have a photorealistic representation of something, and we can easily make, here I draw some bounding boxes around the flowers of the plant, because I wanted to know which parts of the plant correspond to the flowers so that I can maybe count them later or whatever. So yeah, here I'm drawing the boxes, and let me just skip ahead to the final result, which was this. So now we can basically annotate everything in the photorealistic 3D representation and get as much data from this as we wanted. And you can maybe be a little bit inspired for your application, because this is yeah, we can do this with whatever. This is like just one model, but we can make this with entire fields and maybe annotate the type of ground or whatever you can imagine. The possibilities with this, this rendering approach are, I would say, endless. Okay, so this is a small overview of our work that we have performed at the Robotics Research Lab in Kaiserslautern. Here are some references if you're interested. And if you have any questions regarding what I have shown you, if you want to see something in more detail or whatever, you're very welcome to approach me at any time. And with this, I would like to conclude and wish you a very nice FIRA. Thank you very much.
Thank you very much for this very interesting talk. So don't leave right now, because maybe we have some questions. Of course. Ricardo.
Hello, I'm Riccardo from IRAE. Thank you for your very, very interesting presentation. I was wondering, what is your opinion about the use of AI in safety-critical applications? Because if we use AI to detect fruits and weeds, and if they are not 100% accurate, it's annoying, but it's not terrible. Instead, if we use AI in application like obstacle detections, and if they fail even one time to detect an obstacle, or if the model detects, I don't know, a human as grass, we'll have a big problem. So I would like to know if, in your opinion, you would use AI for safety-critical applications like obstacle detection, and how would you ensure the safety of these models? Thank you.
Yeah, I think it's AI is not there yet where it can be solely used as a one element solution. So it always needs to be part of a bigger whole. For safety critical things, let me maybe go back to this video of the tractor. We never just use AI for navigation or whatever. There's always some safety elements involved. And for example, let me just skip to where we see this. So for example, this tractor has a whole safety chain that is completely independent of the AI perception system, and it's actually hardwired into the safety system. So you see this orange sensor right here. This is a 2D LIDAR, which is a laser scanner, which it's not very complicated. It has just one plane of those points that are sent out, but it is validated and very secure, and is directly hardwired into the emergency stop system. And we have defined zones around the tractor, like roughly 1 meter in front of it. So anytime something enters this critical space, the tractor will stop, no matter what the perception sensors will tell it. So we have like this tiered solution. Basically, the high-level navigation and perception is done by AI. But when we go down to low-level security or safety, it's always a system like this, for us at least. And we don't think that AI is able to do this on its own, and always needs some sort of guardrails that are in place to make sure it's safe.
Thank you. Is there any other question? Yes, yeah. It's okay.
Hello, and thank you for this nice presentation. You know, when it comes to agriculture robotics, the first question that comes to my mind is the challenges that you face, especially in the part you showed that you do this navigation and localization in a vineyard with 70% of a slope. So in terms of the precision regarding your sensors, navigation, localization, and this stuff, I want to know what was the biggest challenges that you have, and what is the precision that you need? Thank you.
Mm-hmm. The biggest challenges are, I think, when something goes wrong, in terms of the sensors, as you mentioned. So this, especially the field work, is always coupled with dust, with weather, phenomena that are there, rain maybe, or mist that covers your cameras. And also those LIDAR sensors, if there's dust in the air, they will perceive points left and right that don't really exist in real life. So basically, the challenge is filtering this out smartly, and having algorithms that are robust to these weather and other phenomena that exist on the field. We solved this also in part in simulation. So my colleagues developed some really nice LIDAR simulations, for example, that take this into account. So we can directly simulate this LIDAR relatively physically correctly, and, for example, judge how this dust will affect us. And regarding the precision that we have, well, that depends, of course, from application to application. But yeah, for the vineyard one specifically, we're talking centimeters, because the gaps between the plants aren't that large. It's basically maybe twice the width of the vehicle.
Yes, and we have the time for a very last short question. So feel free. Okay, no question. So everything was clear. You will be free to ask to have some more discussion with Jacob during the coffee break. So thank you again.
My pleasure. Thank you very much.
And now we will switch to the second speaker of the session. In the meanwhile, if Pedro or Pedro, Dinis, Garcia or Mohamed Khan are in the room, please come to me for the following of the session. And now we will have a talk of Sebastian Pütz on universal robots navigation.
Yeah, thank you. Yeah, I'm Dr. Sebastian Pütz from Nature Robots, but we also spin off the German Research Center for Artificial Intelligence, the DFKI, also based in Osnabrück, but also in different locations in Germany. And in Osnabrück, we are, or we could say we are the home of the leading agriculture machinery manufacturers like Grimme, Krone, Amazone, Lemken, and also LAAS. And yeah, Nature Robots is the spin-off, and today I want to talk about what we do actually and where our strengths are. So we see that we need more universal autonomous navigation, which is also not relying on GPS and RTK, so based on LIDAR, for example, in also safety critical environments. So what we did shows this video, for example, so we can drive autonomously over beds, and we have a base station for long-term autonomy, so we provide long-term autonomy based on different kinds of kinematics in robotics, and also support different robots in different environments like agrophotovoltaic. We work together with LZH, for example, Laserzentrum Hannover, building laser weeding. So we also do a lot of these synthetic data tasks we saw in the previous talk, but also do reconstruction of plans and instant segmentation in real time in 3D, and can then detect also some of the diseases, feed them into like into growth application where they then at the end can view the parameters of the plans. Talking about more of autonomous navigation, so what we provide is ready-to-use software stacks, and I will shortly go into depth what we do there. So in different fields we see, for example, in open fields we can draw polygons, and then the route is computed autonomously or automatically, and then the robot can drive it also with different sizes of the handland. In horticulture we always have these beds, so row following on beds, and in orchards and vineyards, we have these perennial structures like trees, bushes, also hopes, and so on. And then when it comes to mesh navigation, so like navigating in really uneven forests or hilly vineyards, but also Moon and Mars or so, then we have something which I want to present a bit more in depth today. But what we do is combining all these technologies with lifelong SLAM, so we can deal with vegetation. So if trees are growing or plants are growing or not there anymore, then that's also not a problem. So for example, row following is something, but also mission planning. When you think of, okay, refill the tank, going back to the home position, and then restart your mission at where you stopped spraying, for example, or yeah, doing autonomous planning, field coverage planning on a field, but also in horticulture, like in vegetable production, small and big scale, whatever, with mission planning. So our system already is running on a lot of robots, and we did some inventarization, weeding, spraying, and also other tasks on more than 200 hectares with more than 500 hours, and our middleware is also running more than 300 robots around the world, not only agriculture. So this is, for example, a short glimpse into what we mean when we talk about field coverage planning. So you can draw a polygon, or you can measure your points with some tool on the field to have it more precisely, and then you can adapt the headland size, and then it's planning the thing in seconds, like the complete route, and the robot can follow also with complex turning maneuvers, and with a precision of 0.2 centimeters, so 2 millimeters of the controller. Of course, there's the uncertainty or precision of GPS and RTK, which comes on top, but the controller is really, really accurate, and then we can do, for example, seeding and then weeding around the plans, what we do with some customers. Then also the field planning is optimized for working on the headland. Going into the depth of mesh navigation and really universal navigation in any structured environments, so what I talked about, for example, in forests or hilly vineyards, we use move-based flags combined with mesh navigation, so this is also available in GitHub. So look into that if you like. We presented that already in 2017, in 16, in Madrid, but also Vancouver. And combining these, so move-based flags is like a middleware navigation system. So when you think of integrating your application in navigation, so navigation needs to know about your application. So when to start spraying, for example, or when to pick the apple, when to pick the package in warehouses. So always navigation needs to be incorporated in that. Combining with this with the underlying map representation, for example, meshes, we lead into a universal navigation system. We need some tools for interacting with meshes, for example. These meshes can be created online, but also offline, with LIDARs, for example, or some tools we saw in the previous talk. And for that, we collected also some real-world data sets. You see here, for example, a field with a barn or a forest mesh data set, like a market garden data set with beds and a potato field, but also in the urban environment, so with tunnels and ramps, which is highly sophisticated. So, and then we also need to adapt path planning on that, because state-of-the-art is doing things like Dijkstra, planning along the edges of the mesh. But what we actually need is planning over the surface of the mesh. So we need some of these algorithms we call also geodesic path planning algorithms. So here you see like an overview of all these path planning algorithms we know, which are out there. And then we adapted from known path planning algorithms from like the history. When we look into that, it's an old topic, yes. Since 1985, there are some geodesic path planning algorithms already. So we did our homework here and developed then the CVP, the Continuous Vector Field Planner, based on the mesh fast margin method, which is originated in 1998 by Kimmel and Sebastian. And there has been a lot of more geodesic path planning algorithms, and then we presented that one in 2021. So what is geodesic path planning? It's unfolding the mesh instantly when you plan along the surface. So it's not the red path here going along the edges. No, it's going over the triangles, going over the surface. And there has been some proofs in 1987 that shows that when we unfold two triangles along a common edge, then the shortest path is always the direct connection. This has been used in computer-aided design like CAD, but also medical imaging, flight simulation, and so on, but not really in robotics, and also not in applied robotics in outdoor or agriculture robotics. So, but we did that. And then you can see here, for example, the result. So at the end, you can query each single point on the surface, and you will get the direct vector to the shortest path to the goal on any position. So the vector field is much more valuable as a pass compared to the pass. We also incorporated then like obstacles computed by height differences, for example, roughness and steep slopes, whatever you can imagine. You can also incorporate semantic meaning. So if you detect with an AI, so for example, there's something which should not be drive over, then we can put this into the map. Doing this, we can then navigate alongside the obstacles, around the obstacles, and compute these maps in under seconds. We did some tests years ago already. So in 2018, with our campus data set, urban test environment in Osnabrück. So reconstructed that to a quite huge map. And then we also have these tunnels in the map, in the mesh map, and some ramps. And when we can compute a pass from the lower level, so from the parking garage through the tunnel, along the ramps to upper level in under a second with the continuous vector field planner. So seeing some results compared to Dijkstra, we are actually much better in terms of the length of the pass, and compared to the exact shortest pass, we are get almost the same length as MMP, like the exact shortest pass. We applied that in the forest, so showing that we can also apply this on any other environment. So for example, on the field, we also did that. But here the robot is equipped with a LiDAR, so it's localizing with a LiDAR, because in the forest you have no proper GPS and RTK localization, right? So it's localizing in the map with the LiDAR and then driving alongside the vector field. And the vector field is computed in under a second to any goal position you want. And the nice thing, so if you move the robot from, let's say, one position to a position which is like a meter or 10 meters away, then it directly knows again where it needs to go, because you have this vector field. And here you see what is drivable and what is not. So here are some boring results. So you see that this approach is always better than the state of the art, and we get really nice smooth paths over the surface. And at the end, I will also show some localization approaches. So here a machine is driving autonomously through an orchard, or that's actually a tree nursery. And the system is localizing only using LiDAR, 3D LiDARs. And the nice benefits are we get a 3D map out of it, where we can then do tree analysis, for example, but also using this map to derive the rows for mission planning at a later stage. We did that also in an orchard. So here's the orchard. So the machine can drive along these rows without GPS and RTK, which is often a problem when the trees are somewhere block the signals or shadow it a bit. So it's much more robust as just using GPS and RTK, and then the machine maybe needs to stop. Of course, you can have some reactive row following, but it's like a more universal approach for navigation. Yeah, thank you very much. Here should be some logos.
Thank you very much for these nice presentations. We have time for one or two short questions. Yes, please.
So thank you for this presentation. It's very interesting. I have one question. about the limitation of LIDAR when passing through very early stage plant. So the precision of LIDAR, when we can start using it for passing in a row like a corn field or something like that. And thank you.
Very good question. So what we actually did is, so we have a hybrid localization. So on a huge field, you can use GPS and RTK. It's pretty much usable there. And where you can't use it, there you also have then these features which are important for using SLAM, lifelong SLAM. So this answers your question. So in these areas where SLAM is strong and it's required, there we have it and can use it. And if it's not usable on like really huge fields where almost no features are, then you use GPS and RTK. But of course, you can also think of like a cornfield or so. You can also create your own structures and localize in your structures. So while harvesting, for example, of course, that's difficult and security difficult field then, but yeah.
Okay, I'm sorry, thank you very much, because we're going to have to save time and to keep the time. So if you have other questions or discussions, you can join us during the coffee break. So thanks again for this nice presentation. And now it's time to talk about the point cloud harvesting. And the third presentation coming from the LAAS in France, of course. Some technical issue. Perfect. So, Harold, the floor will be yours in a few seconds. And it works.
Thank you. Good morning. My name is Harold MURCIA from our RIS team at LAAS NRS here in Toulouse. Today, I would like to speak about my project concerning the use of light detection and ranging devices on board robots for ORCAR monitoring. And to allow in this presentation, I will focus on 3 key questions. First is, what can LiDAR do for ORCAR monitoring? Second is, why is LiDAR the right tool for the job? And especially, with some examples, how can we use in this kind of applications? Okay. So thanks to the previous presentations, as you know, LiDAR technology or laser vision systems are very useful for mobile robotics and navigation and obstacle avoidance. However, with the same sensors, we can exploit this data from the point of view of remote sensing. And we can use this data, for example, for determine some important features for trees, in the case of orchards. For example, we can generate digital elevation models from agricultural fields of our terrain. Also, we can use for weed detection or tree identification. Then, at tree scale, it's possible to determine some measurements important for the trees, like altitude, trunk diameter, crown diameter, canopy volume, and others, or structure analysis. And also it's possible with more detail to use for fluid detection and location. And also it's possible to perform models with this data to estimate on important phenotypes. For example, in the case of yield estimation, biomass estimation, leaf area density or leaf area index, which is very important to determine some photosynthetic activity of trees. And with all this information, we can help to facilitate key agricultural decisions, like, for example, water use optimization, localized application control, planning, pruning, or even to assess the climate impact. But the question is, okay, why LiDAR? What is different with respect to other sensors or devices? Well, LiDAR provides three-dimensional information in a natural way. That means that we don't need any additional processing step to generate our three-dimensional data. And it's not affected because environmental light or changes of environment. That means that our robots can operate without any time constraints. We can work at any moment of the day or night. And also because it's effective in deep vegetation. So we can penetrate the vegetation and determine hidden details that is not possible to detect with other or with regular sensors, not so easy. So let's focus on the core section of this presentation, is how to put LiDAR in action in this kind of agricultural applications. To do this, I will introduce our proposed framework with 5 simple steps. Then I'm going to present some results for each step to conclude with the summary section before questions and answers. Okay, so the proposed framework starts with a pre-processing stage. So basically the question here is how to generate a three-dimensional model of the orchard. And the idea here is, okay, we have the LiDAR, we get the data, but we need to combine all these LiDAR scans from the moving robot in a perfect alignment so it's possible to generate a three-dimensional representation of the orchard. Once we solve it, then we start with the information extraction stage with the semantic understanding, addressing questions like, where are the trees in my point clouds? Where are the weeds? What is the shape of my terrain? Or what is the inclination of my terrain? Here we add a label to each point from the whole point cloud, so it's possible to distinguish between ground, trees, and weeds. And then we use tree isolation. We separate each point cloud for the individual tree. Then it's possible to determine how many trees do we have in our orchard. Then it's possible to know, to determine or typify our tree. So we can have measurements like altitude or any other phenotype we are interested. And it's possible to know how good is my tree, to check our tree in an individual or single one-by-one process. And at this point, we sometimes have some outliers and some atypical elements. It depends on the data used for the training or our experiments or our orchard. So sometimes we need to remove some outliers and filter to focus in the real trees. And at this point, we have 2 options. If we know what are we looking for, if we are interested in determining some phenotyping analysis or some key agricultural decision, well, we can do it. In other case, we can apply some variability analysis to know where do we focus our attention. That's the sample that I would like to present today. And this is the simple proposed 5 steps framework. But before going with the results, one of the most common question I have when I speak about this topic is, okay, but how do you generate a three-dimensional reconstruction? Here's the answer. It's very simple. We are using in our experiment ROS, which is a robotic operating system. And basically, we put our robot into the orchard to navigate the orchard, collecting data. So, of course, we are collecting scans from the LiDAR, but also we are recording data from the navigation sensors, GPS or IMU. So then, in a first step, we fuse navigation data coming from latitude, longitude, altitude, and orientation with Kalman filter to generate a transformation matrix. And things that all our sensors are perfectly synchronized, we can assign a transformation matrix to each scan. So we transform the LiDAR scan from the local sensor to the global sensor. And we can generate this reconstruction. As you can see in the right side, we have a fragment of a reconstruction of our parking lot in the laboratory here in Toulouse. But however, if you note, we have some error, especially you can note in the trunk of the tree or the lamp, we have some distortion. So then we proposed a second stage, post-processing, by using the same information from the LiDAR. In this case, we are using visual algorithms, which is iterative closest points with postgrad optimizations. And then we can redefine our transformation metrics, and we can improve both the quality, the position of the post-estimation of the robot, but also we can improve the quality of our three-dimensional reconstruction, as you can see in the last picture. So well, once we have the whole point cloud from our ORCAD, then we can process with the analysis of the artificial intelligence methods. So in this case, that is the first example, is the first trial experiment. In this case, we are using an aerial platform. So in the left side, you can see the LiDAR on board the drone. At that moment, we were using a low-resolution LiDAR, a QuanEnergy LiDAR, and with an experiment around 20 meters with respect to the ground in a citrus orchard in Colombia. And the results at that moment was around 800 points per square meter. It's not too bad. From aligning approximately 200 scans. So on the right side, you can see the fragment. This is 3D, but it's difficult to put 3D in this slide. So this is a top view of the three-dimensional reconstruction, where the color is the altitude. So you can see in blue, low level, and you can see the trees from the experiment. In a second iteration here in Toulouse, in an apple orchard, close to behind this building, if I'm not wrong, we have a second iteration. We improved our system. So in this example, we have an Auster LiDAR with higher resolution. In this case, it's a ground robot from our laboratory. And as you can see, we improved our resolution. So in average, in this case, in this example, we have around 40,000 points per square meter, which is nice. And by aligning approximately 400 scans. Yeah. In the left side, you can see our experimental setup. On the right side, you can see the top view of the generated point cloud from the apple orchard. With around, for a total, in this example, the total number of points is around 30 millions of points that we need to process later. So then, once we have the point cloud, I will focus on the apple experiment. We can use some classifications algorithms. In this case, we are using deep learning with the RAN-LA-net. It's a supervised classifier. And at this moment, in the same top view, you can see three colors. That's the prediction. So in blue is what our model defined as ground. So it's possible to determine the terrain digital elevation model. In green, you can see what our model interpreted like wheat or grass. And in red, we can see our trees. So then we split our trees and we isolate in individualization. So it's possible to analyze our tree one by one. This is by using a very simple algorithm, which is DV-scan. And we split our trees. However, as you can see in the orchards, sometimes we have some elements. This is individual. This is the result for some individual clusters. In theory, trees. But as you can see, we have one tree and two imposters. I cannot tell you who is who. But I will explain you later how can we filter. So that's one example of our individual clustering results for the orchard. And then we need to process to analyze the data. Today, I will focus just in the structure analysis. So basically, we take each tree and we apply some skeletonization methods. So we can reduce the point cloud, focusing in the structure. And then we can have a second representation, which is a graph representation. You can see in blue some segments, and in red, in red points, the bifurcations of nodes. So we have information about the structural and the main branches of every tree that we have in our orchard. Then we reduce our first point cloud from 1,000 of points to just process 100 of points, which is easily with the significant information. For this example, we can use very simple features or descriptors. In this case, we are using a spatial structure, branching geometry, symmetry, and complexity. So we can build for each tree a feature space, a representation of information for each tree, and we can compare. With this information, for instance, we can filter what for us is trees, and we can filter our outliers or imposters. So as you can see, some red points, we filtered or we removed some outliers, which for this example, we had some big weeds, some dead trees, and some poles, which was in middle of the orchard. So it's possible to focus just in the regular trees. And well, with this information also, as I mentioned before, we split the outliers, but it's also possible to determine a variability or a spatial variability analysis. So what I did here was just fuse the feature space, and then we can determine, this is also a top view for our orchard example, but we can determine where do we have some variability. In this representation, blue represents the low variability, and red means the places when we have high variability. So it's possible to know where are our trees, where do we have outliers, or where do we have some pattern of heterogeneity. To summarize at this point, today I proposed here, I show you some framework process for LiDAR data on board robots with some main steps like 3D reconstruction, semantic understanding, tree isolation, and individual characterization. The experimental validation was with around 40 trees here in Toulouse, both with analysis at single scale for each tree and also a general view of the orchard with the spatial variability map. For future, at this moment, we have some modular and adaptable framework, which is possible to scale across different platforms, also to scale to different and larger scale orchards, or integrate with other agricultural systems, at least I would like. And we still having a need for data, because all these methods and experiments that I presented here today are based on data. However, with LiDAR, it's a little bit more complicated, and it's difficult to find labeled or coherent data with agriculture, real examples. And also, just to mention, the results that I showed you before is just with a fragment of the 100% of the collected data. However, if we increase the amount of data, of course, we have more information, more detail, but we increase also the computational cost, which is an open challenge when we work with LiDAR information. So thank you for your attention, and any comment or question is welcome.
Thank you very much, Harold. We just have time for a very short question because time is running out. Is there any fast question? Yes? There is some free space at the front of the room.
Thank you very much for a nice presentation. I was wondering, how would you deal with overlapping tree instances in this case? So in your orchard, the trees are nicely separated, but in a lot of orchards, vineyards, for instance, and in the Netherlands also orchards the trees are not completely separated. So how would you deal with this challenge?
Yeah, it's a good question. It's true. Fortunately, in orchard, we have some distance between trees, so it's more or less easy. However, sometimes, for instance, in vineyards or even in forestal applications, we have this overlapping problem between the trees. So it's a little more difficult for our algorithms to determine to separate each tree. But however, depending on the quality of data, we have some experiments, and it's possible. The thing with this is that we need more resolution to solve or to face this overlapping problem with the trees.
Thank you very much.
Okay. Thank you very much.
Thanks again. And it's time for the next speaker, Pedro, Dinis. I was looking after you. We will talk about IoT, AI, and robotics for sustainable agricultures. In the meanwhile, do not hesitate to come in the front of the room. There is a lot of space. And Pedro, the floor is yours.
Okay, thank you so much. Good morning. See, I start this presentation with this slide. And this slide is a buzzword of what we are doing here. So I will present some of our projects and the results of our projects based on all of this. So monitoring, sustainability, smart digital, artificial intelligence, rural and agriculture. So you have here a lot of information. But what is the main issue here? So the main issue is to integrate all of this. The IoT, the AI, and the robotics in order to enhance sustainability, agriculture, and also ecotourism. You will see what I will try to do about this. And of course, let me show you, I came from University of Beira Interior in Portugal, and I will present here the results of 2 projects. And the first one is Robotics. So this is an international project with Spanish and also French partners. And the idea is to enhance the competitiveness of and growth of SMEs in the Sudway region by modernizing agri-food and plastic sectors. So our presentation here is about agri-food and mostly applications where we can improve this solution. As you see here, so these are the partners along the 3 countries that are on this project. So us, another partner from Portugal, and then universities and institutes from Spain and France. And what is Robotics? So after we pick up the fruits, and we can see the pickup or picking the fruits in the orchard or then in the warehouse, we need to handle these delicate products. Okay, so if we are talking about fruits, they are delicate, and you need to handle it delicate. So, and the current solutions are both expensive or not suitable for small and medium enterprises. So the soft grippers that we are now proposing are developed in TPU. So we can do it on additive manufacturing. So it's very, very low cost and very simple to do it. And then we use also computer vision systems in order to identify the defects in fruits. I will show you how we have done this. So in terms of the manipulation task, the objective was to design and to build a soft gripper that was capable of sensing the deformation. So what are we talking about here? We are talking about a gripper that is a self-sensing gripper. Okay, so you don't need to use or to include a sensing device in it. Okay, and how have we done this? We have done this exploring the TPU behavior for robotic applications, and then we improve it for quality control in food sorting, and then for a cost-effective solution and methods that are accessible for SMEs. And the first thing is, how have we designed it? You find in literature several solutions based on this. So this is a fin ray effect gripper. And with this structure, with several cross beams and a rear side and a contact side, you are able to involve all the product. And what we have done is to explore some design variations. So with uniform thickness, but without cross beams, with different thicker rear side and no cross beams, and mixing all of this, okay? And the results are tested experimentally and also numerically. So we developed several numerical tests using ANSYS and using also TPU Filaflex 95A. You will see that afterwards we tested other materials, but this is one of the best. And we use FFF technique for 3D additive manufacturing. And when we compare the analysis of the material, we get very good results approximating the material behavior in terms of stress and strain with relationships about the different model predictions. So we made some simulations. As you see here, these are the results of the different grippers involving this kind is a perfect circle. And with this, we get results from the linear actuation and the rotational actuation, depending on the type of the finger. Okay, and they provide here the angle, the best angle, the grasping angle for all of them. So what we want the higher grasping angle, because if you have the higher grasping angle, it's saying that we can cover all the object. And then, okay, but we tested and produced in additive manufacturing several of these fingers, and what you see here is that if you do it with a conductive filament, you get a result or a variation of the electrical resistance from the deformation. And so this is a piezoelectric behavior that is here provided. And with this, we made some tests to correlate force with the analog to digital converter values. So we measured all this information using first a weighting balance, and then the solution that is provided here on UR3E and with a NESP 32. So we made the calibration of the loads through the reference force sensor. Then different tests were conducted with different amplitudes and speed. So the idea was to verify if the different amplitudes of the force and also the speed that we pick up the fruit had any difference, and recorded these values. And these are the results. And what you can see here is almost a perfect relationship between the force and the ADT values. So we have here percentual deviations that are very small and that provide a very good result on the gripper deformation sensing. And how have we improved this? First, on the development of prototype grippers with the inclusion of vision sensors. So here is an image. So we have a camera in the bottom of the gripper, and with this we are able to pick up with delicate, in this case the fruit, and also apply some artificial intelligence algorithms in order to detect imperfections, to detect defects on the fruit. So we made here this design, so with multi-material self-sensing, and for this we enclosure all the data acquisition system within the gripper, as you see here. And we also developed, in this sense, we name it as LITEX from our laboratory, that is the Laboratory of Innovation and Technologies in Sustainability, an IA vision that is able to detect, in this case, pitches in the warehouse, and also detect the defects that it has in it. So you have here some examples. So we tested with different fruits, peaches, in other, in this case there are rubber fruits, but we developed in several tasks, and you see here the solution. So this was one approach directed for the grippers to pick up the fruits. And we have another project that we name it Montaña Viva. And it's somehow in this, what we are talking here is somehow different. Because the idea here is to integrate not only agriculture, but the monitoring of the plants, but also with an ecotourism version. And all of us that are here, we know that right now there are several agricultural applications that can be parallel with tourism application. And for this, and in the context of mountains and plants, and this is directed for mountains, we are here to present somehow a different approach for it. One thing that I saw here in the previous presentations, and some of the difficulties were already exposed, is that everything goes well, or most of the time everything goes well when we have right and direct trails without irregular paths, if the weather is fine, without dust, without mist. But in the mountains, in the agriculture fields, we have that. And the idea here is somehow to improve the accuracy of the predictions. And for that, what have we done? We found in the mountains some indigenous plants, okay, so they are wild plants, but that wild plants may have some food applications or some aromatic or some medicinal applications. And depending on that, we select them, and afterwards we include technology and local agriculture on this ecosystem. So the idea here for the farmer is the farmer to plant these wildflowers or these wild plants, and in that way also have monitoring devices that are able to have both agriculture application and tourism application. You are all aware of this, so local and geospatial sensing using all kinds of monitoring stations for temperature, humidity, precipitation, wherever. You can have it all because you know this. But what have we done? We have performed here or developed a monitoring station that, besides all the sensors that are modular, you can place it and take it out depending on the solution, we integrated satellite IoT communication. Okay, and as you know, when we talk about agricultural fields, we have a lot of agricultural fields that we don't have communication, we don't have Wi-Fi, and how do we communicate the data? And this is an approach. Instead of using or placing antennas, we can use LoRa, and LoRa will communicate with the concentrator, with the hub, and then the hub communicates with the satellite. And then the satellite gives again the information for any cloud server. Besides that, we developed here an interactive dashboard. So this interactive dashboard covers all the information of the sensing in real time. And for this specific project, that remember, the idea is to relate agriculture and tourism and wild plants. We perform here a source of gamification based on the plant identification technology. So what is the approach? We developed this interactive table, and with this, we have focus on the indigenous plants that have potential applications. You have here some of these wildflowers that can be used for health and well-being. And we found therapeutical potential in some of them. And on these wild positions, we placed the monitoring station. And the monitoring station is able of doing what? Besides picking up all the information about the weather and the soil, is also includes a computational vision module that is able to detect the phenologic state of the plant. And with this, you can see if the plant is growing, if the plant is flowering. And when the plant is flowering, since it's an indigenous one, you can have related in a tourism app when you say the tourists go and follow this path, because if you follow this path, you will find an indigenous plant that you can only find in this place that it's now flowering. And for that, we used artificial intelligence algorithms. So in terms of the project impacts, we recognize and map some places. We involve and co-create with the region actors and capacitate and disseminate these results. The main objective of this and the main outcome is that we can replicate and value the natural mountain sources, and this to enhance natural heritage. So here are a final acknowledgements, and right now I'm ready for your questions. Thank you so much.
Thank you very much. Unfortunately, we won't have time for this question because we would like to, to preserve the opportunity to have a coffee break. But we're going to have time during the coffee break. So,
of course.
Thank you very much again.
Thank you so much.
And let's switch to the last presentation of the first session, which will be given by Mohamed Khan, about how AI can accelerate autonomy.
Okay, so thank you so much for the opportunity to share this project with you. I was here last year as well, talking about routing, and this year we're talking about routing at scale, and would love to share more information about this project that started last year, and it has gained a lot of traction over the last 6 months. Okay, so how did this particular project start? The motivation actually came from research organizations and policymakers in agricultural space. So Verge Agriculture was approached by PAMI in Canada. So PAMI is Prairie's machine intelligence institution, which is one of the premier institutions on agricultural research and agricultural machinery research. And they wanted to conduct a study of what would be the productivity impact and sustainability impact of draining wetlands in Saskatchewan fields. So Saskatchewan is in Canada, it's a province in Canada. The agricultural fields have a lot of wetlands, and the government is interested to find out what would happen if you drain, let's say, 25% of them, or 50% of them, or all of them. How much productivity would you gain versus the environmental impact of draining those wetlands? And that basically requires you to simulate the movement of agricultural machines at scale and doing so with all the wetlands, and then doing so with a subset of the wetlands, and then doing so with a smaller subset of wetlands, and so on. So this was one problem that came to us, and they wanted to perform the analysis of 25,000 fields, which is massive data set. But this wasn't an isolated instance. We had a similar request coming from Grain Research and Development Corporation in Australia, who wanted to conduct a study of controlled traffic farming. And doing so, again, at scale, like in an Australian setting, in Australian farms, what if you implement controlled traffic farming? What will be the productivity and, again, sustainability impact of doing so? And then what if you have autonomous machines, fully autonomous? You have robotic swarms working in Australian fields. What would be the environmental impact, positive, negative, and what would be the productivity impact of doing so? So these were instances where you can answer these questions by performing routing or path planning of agricultural machines at scale. And at the time, we had a solution for growers. We had a routing solution for growers and for individual fields or farms, but not at that scale. So that necessitated this project, like how are we going to scale this to thousands of fields in real time, or hundreds of robots in real time? And the answer was that we can't really do it very efficiently using classical methods. So it would take you days, or weeks to run this sort of simulation and process all the routes for, let's say 25,000 fields. So we started looking into quantum computing. First we started looking into parallel computing, then we started looking into quantum computing. And over the last year, this project developed and we achieved this routing at scale over the last 6 months. So let's jump into it. The outcome of this project has been world's first customer-facing quantum-powered application. So quantum computing is considered a future tech. People feel that it's like 5-year, 10-year, 15-year away. And it is true for the gate-based quantum computing. But there is another quantum computing model called quantum annealing, which we have been able to leverage today and productize. And the result is that we have a customer-facing product that is powered by quantum computing today. It is the world's first because all other applications of quantum computing have been internal. Some organization is doing some internal optimization and experimenting with quantum computing, not to a customer-facing setting. So this is pretty unique. And these are not my words. These are the words of Canada's digital supercluster. It's a major funding organization in Canada, and they are supporting our project. And recently they did a big press release around it, and they're very excited about it. They called it world's first consumer-facing quantum product. Let's dive into the solution. What is the solution? Okay, so these are the technological components. So I'll try to keep it as simple as I can. And it really starts from the right. It starts from the Verge's Launchpad, which is an operational planning solution. Okay, so you can bring your boundaries, you can plan your operations, and then you can push routes to autonomous or semi-autonomous machines that will then execute those routes in your field. Launchpad also takes care of handling terrain, boundary processing, all the stuff that is needed to make routing happen. And through Launchpad, that's how the customer, the end user, like PAMI, is going to interact with the routes and with the analysis. So all the data comes from Launchpad, okay? And Launchpad has the ability to detect agricultural boundaries from satellite imagery. So PAMI, for example, doesn't have to provide us the boundaries of Saskatchewan fields. We can extract them directly from satellite imagery. And we can do that in North America, Europe, Australia, and extending it to Asia as well. So once the boundaries are extracted, they are sent for routing. We can do routing using ant colony optimization and some exact methods, and there are some other heuristic methods we use as well. And that's where we started from. So when we're doing routing for a single field or for a farm, we use ant colony solvers that we have developed. But now we're talking about scale. So how do we do it for 25,000 fields? We send the problem to the D-Wave quantum computer. So D-Wave has a 5,000 qubits quantum annealer, which is the biggest scale of quantum computing that's available today. And quantum annealers are great at solving optimization problems. They don't solve all problems. For that, you need a gate-based computer, which is, as I said, it's going to take 5-10 years for us to get to a scale with gate-based computers. But with quantum annealers, we already have a 5,000 qubit scale, okay? And that's what we use to solve the problem at scale. But there is an intermediate step, and the step is how do you take the problem and model it in such a way that you can leverage classical as well as quantum infrastructure to solve the problem. And that's where this platform Super comes in, which is a modeling platform. So D-Wave team, worked with the Stack team and used Super to model the problem, which is basically a vehicle routing problem, a capacitated vehicle routing problem, and casting it into a form that can run on quantum computers. Because you can't just write code and it's going to run on quantum computers. There is a big gap between what runs on a classical computer, what runs on a quantum computer. So this problem translation from vehicle routing to quadratic unconstrained binary optimization, or QUBO, is key. And doing so in such a way that it's feasible and performant was the key step. So we do that using Super, and then the code gets deployed on the D-Wave quantum annealer, which is available through Leap Cloud. So, I mean, you can experiment with quantum computing. It's available through the cloud. So sign up, go to D-Wave and sign up with Leap Cloud and start experimenting, really. Once the code is deployed there, job runs, you get the results, and then the results are sent back to Launchpad. So customers and end users interact with the results through Launchpad. And then they can be sent to machines. You can push the results to the machines, export them, and the machines will execute them in the field. But in this particular project, the emphasis was on the simulation and analysis of running those machines in thousands of fields, basically. Okay, so the results we got were very encouraging. So I'm not going to go into a lot of detail about the results, but basically what we found was that we can achieve a 5x speed up. So within the first 3 months of starting the project, we were able to get a 5 times speed up using quantum computing versus using parallel compute and all we could from classical machines. Okay, and now we have pushed it further to 10x and even more. So basically, to simplify it, in a 2-second interval, we can plan about 100 fields, and generate routes and send them to whoever needs to use them. Which then means that for thousands of fields you need a few minutes, whereas on a classical machine you would need days, or even on a classical cloud you would need days to perform that analysis. So that's the result. And we had a number of formulations. We had a serial quantum formulation. We also had a parallel quantum formulation. And that's the parallel quantum formulation that allows you to get the most speed up. And the objective values are same, are quite similar for the ant colony solver that we had and for the quantum solver. So basically we maintain the quality of the solution and speed it up, 5 times, 10 times, to get the scale that we need. So I have a demo here. Hopefully the video plays. Okay, here we go. So it starts with the boundary detection. So suppose you want to perform an analysis for a whole province or territory. You start by automatically detecting the boundaries. So they are not exported, you detect them. Then you select the boundaries you want to perform the analysis for. So in the video, we're selecting a small number, but in the project, we're doing thousands. And then you run, you provide machine parameters and you run routing. So you can choose an operation type, machine type, section control, all the different parameters. You can use the terrain information. In this demo, we're not using terrain information, but you can. And you get a path plan first, which is parallel tracks, and then you get a route, which is end-to-end line string, from a start point to the end point. And this is a simulation that shows how the route will be navigated. Okay. Now, these are all very simple fields, the ones you're seeing. So after this, you're going to see a complex example. What happens when a field is like a Swiss cheese? You have a lot of obstacles, and this is where the routing problem becomes complex. And these are the kind of fields we were dealing with from Saskatchewan, the ones with wetlands. Okay, so let's see how this works. And those who work on the routing problem or path planning problem know that now we're in the NP hard territory. So it's hard to find an efficient solution. So you have to use some heuristic like ant colony solver or some such heuristic. So now, yeah, this is the route, and now this is being navigated. So you see the tracer that shows you how the route is being navigated. So if you choose a different start point, you can do that. A different start point, different end point, the route would adjust accordingly. And it will try to find the best way to navigate from the start to end point and minimize the number of double maneuvers. Or it tries to avoid from passing through an area that it has already serviced. That's the idea. Okay, so it leaves a few tracks on the top because it needs to get back to the end point. Okay, so if you change the start and end point, this routing will change. So here we go. Now the route is complete. So yeah, this is just as applicable for a single field. If you want to plan a machine route for a single field or a farm, and also applicable at scale. Okay, so just quickly providing some more info. This FIRA is actually part of a speaking tour where we're going to talk about this and other quantum applications that Stack and D-Wave has been working on. So the next one is going to be in LEAP in Saudi Arabia, then Qubits, which is a major quantum event, and then in Ventures. So hopefully you can follow along on that front as well. Project team. So Verge orchestrated the project. Verge is the precision agriculture company that's at the center of it. But then we were supported by this whole ecosystem. So on the quantum side, we had D-Wave and Stack taking the lead. On the customer side, we had PAMI and GRDC. And then on the research side, we were collaborating with the University of Northern British Columbia Computer Science Department. And on the funding side, half the money came from the industry and half the money came from government, from the Digital Supercluster and MITEX. Both of them are in Canada. And in terms of our impact, so right now, PAMI is using it. GRDC and ACTFA in Australia are using it. And now we're making it available, as an API. So, if you are interested in running our routes on your machines, let's talk. We'll make it available to you. You can run these routes on your machines and see how good they are. Okay. In Brazil also, we have AgroSure using our solution. And with that, thank you so much.